All right. Well, thank you so much for coming out. It's a real privilege and a pleasure to speak to people who actually get paid to work on Linux. I have a System 76 laptop, which is a Linux laptop. Thank you. It's my weapon of choice, and I have a System 76 desktop at home, which did a lot of the work that I'm going to talk about here. But I've only been using Linux for 14 years, so I feel like a bit of an imposter here. But it's an incredible operating system. I was just talking earlier about this. It's kind of amazing that Linux forces you to work on cool stuff, because the boring stuff doesn't work so well, but the cool stuff does. So I guess part of my talk here is kind of a call to action to take your skills and apply them in the real world. And of course, Linux, in many ways, has been built by hobbyists and people working in their free time. And the projects that I'm going to talk about today were largely projects that at least began as kind of free time, spare time projects. So I'm going to speak about 3 separate things that I've worked on over the years, and a couple of words of biographical introduction as well. But first, it's important to have at least one slide that is a wall of text. And so I'm not going to read all these out, but on the left we have a list of Robert Boyle's list of scientific projects. And of course, Robert Boyle, I think, holds the record for discovering the most elements of any of the scientists back in the time when you could discover elements. I think he discovered like 14 or something. And back then, which is about, I'm going to say 1820 or thereabouts, he said, wouldn't it be cool if we could figure out how to prolong life, figure out how to fly planes, make submarines, flexible glass, various advanced pharmaceuticals, perpetual light, the attaining of gigantic dimensions, and all that kind of stuff. And then I kind of made my own list about a year ago of projects that I thought we might be able to address in our lifetime on the right. And some of them are more whimsical than others. Obviously solar power, fusion, better AI, terraforming, tunnel boring, machine mining, zeppelins, post-scarcity and transhumanism. And I think it's actually super exciting that we get to live in 2024. I know most of you are probably bought into this, but if you've ever done any genealogy or anything, you'd probably appreciate that the lives we live are unspeakably charmed by the standards of any reasonable historical comparison. One of the projects I'm going to speak about is the Scroll Prize, which refers to these artifacts that date back 2,000 years. And the richest people in ancient Rome, hell, the richest people here in Pasadena 50 years ago had worse access to just things of extreme luxury that we take for granted. Like I fly home to Australia once a year. Like, that's crazy. Robert Boyle would lose his mind. And of course, lastly, the XKCD cartoon pointing out that radioactivity is still, we don't know what to do with it. So this is a Mid-Journey generated image of kind of a nice-looking futuristic city. Obviously, opinions on aesthetics differ, but this kind of is a vision for what I hope that we can agree would be good to build toward, which is to say, a future where there's lots of greenery and plants, and we're environmentally conscious, and we have urban spaces that encourage life and human interaction. And at the same time, we are finally finding ways of building buildings out of glass and concrete and steel that are less boring. And humanity as a whole, has this kind of incredible opportunity and wealth spread all around the world. And the cool thing is, like, I'm in decent health for a man in his mid-30s. I think there's a good chance that I will live to see a world that looks a lot more like this than the world we're in right now, let alone the world of 1970. And this is super exciting. Here's some biographical photos. Some of these are kind of old, but essentially, when I'm not hacking on computers, I'm either climbing mountains or exploring Siberia or jumping out of planes or whatever. Or volcanoes, actually. I mean, like, don't sue me, but if you have the opportunity to see an erupting volcano in person, definitely do it. It's the second most spectacular natural occurrence that you'll ever see. The other being, of course, a meteorite impact, but those are hard to plan for. So I came to the United States from Australia in 2010. I still celebrate the day I arrived. Show of hands, anyone here who's an immigrant? Oh, great. Well, welcome to the United States. And it's really kind of an extraordinary thing that people can come from all over the world to the United States, sometimes with a little difficulty. and build a world for themselves here. I've been here for 14 years. I'm naturalized. I can vote now. But I came out in 2010, and this is the peak of my academic career, which is when I managed to get this figure into a journal. And it shows me and my advisor fighting with lightsabers, and another advisor shooting force lightning in the shape of a gravitational wave signal that was detected from a black hole binary in spiral. That's kind of pictured behind the lightsabers there. And Disney did not sue me. So actually, I think this was before the sale, but this is relating to some rather esoteric work that I did in grad school, again using Linux, of course. But we were simulating these black holes colliding, and just to give you a flavor of how annoying and difficult that is, if you just kind of set up your black holes in a default coordinate system and press go, the coordinate system gets eaten by the black hole. So like all your coordinates just kind of fall into the black hole and it breaks. So an awful lot of very, very hard work was done there over the years, and I was kind of fortunate to play a small role in that. Although I did leave Caltech the same day as the detection of this gravitational wave signal, the first ever. So that was poor timing. I left Caltech, I left academia. I wanted to work in hardware. I was inspired by what JPL does and what SpaceX did, but I could not work at the time on rockets because I did not have a green card. So I went and worked at Hyperloop One, where I was a levitation engineer working on magnetic machines. And well, Hyperloop kind of went through various cycles, but we did manage to build this incredible test rig out in the desert near Las Vegas. And again, like the gentleman you can see next to me in that photo remain good friends to this day. Some of them, I think, even work for me now. Yeah, one of them does. All right, after that, I went to JPL. Most of you will know this, but JPL is just up the hill here in Pasadena. It's the NASA center that specializes in deep space robotics. And on the top left, you can see me on my first day, and on the bottom left on my last day. So I was there for about 4 years. And one of the amazing things you can do at JPL is as an employee and even as a tour guest, you can walk through a gallery that overlooks the high bay, which is this central picture here that I took when they were assembling the Perseverance rover, which is the most recent Mars rover, which we'll talk about a bit later on. And then in the top right, there's an image of the sky crane, which is a component of that rover that basically lowers it down to the surface. And in the bottom right, an image of the sky crane in action. This is a photograph of an alien spacecraft, an alien robot landing on an alien planet. And the colors are perfect. And even though the rockets are firing, you can't see them because Mars's surface is practically a vacuum. Yeah, it's kind of mind-boggling that this can be done at all. But my wife was actually involved. She worked at JPL as well, and so we were working from home in the pandemic when this happened, and she was one of the first people, and me standing behind her desk to see this image come down, which is cool. Anyway, JPL was fun, but ultimately it was not really scratching a deep itch I had, which was to really kind of cut my teeth with difficult management challenges. And actually, some of you I know will have experimented with entrepreneurship. I wouldn't necessarily say that you definitely have to do it, especially if you don't want to. It's one of these things where if you have to be convinced to do it, it's probably not the best idea. But if you have considered at some point maybe starting a company and becoming, a mechanism by which you can help your fellow humans earn a living and build value, then I do recommend it. It's by far the most satisfying thing I've ever done, with the exception, of course, of having children. So on the left is me in my lab coat in my garage, performing benchtop experiments, reviving my first year undergraduate chemistry knowledge. And then in the central and right-hand photos, you can see the castle that we rented or leased in Burbank, where we're building stuff. I'll talk a bit more about this later on, but it's just kind of, I think Linux, kind of echoes this idea. Like Linus had this idea, like what if we could make an open source operating system? And it's obviously an insanely difficult, unfinished project, but he got far enough by himself, not so differently to me with too much hair in my garage, fiddling around with stuff, doing something that he'd never done before because no one had ever done it before, just seeing if it can be done. All right, so onto the matter. What gives people feelings of power? Money, status, and thinking about the Roman Empire, of course. So this is a reference to a meme that did the rounds recently. And on the bottom right, we have an image of a bronze sculpture that was found underground near Herculaneum. in the Villa of Papyri. And then at the top and next to it, we have photos of more contemporary libraries. And these libraries are beautiful. Not every library is beautiful, but these ones are. And the reason they are is that books themselves are fairly undistinguished when they're on the shelf. But the reason that people build libraries like these, and that they built libraries like this in the ancient world, is that if you want to convey prestige, if you want to brag about your wealth and your taste and your skill, then you build a library and you fill it with beautiful artwork and sculpture and books. And books were then not commodified by Amazon. They were extremely expensive to procure and to own and to produce. And so it is not exactly a surprise that when we read essentially the tatters, the remnants of the ancient texts that we retain to this day, we find references to libraries and people who had great reverence for books, who read them more or less continuously. I think Pliny the Elder lived to a relatively advanced age and spent his entire life surrounded by multiple scribes who were either continually reading to him or continually taking dictation. That's how he spent his time. Like this production function of these people, they kind of knew what it was about. Anyway, so it turns out that Calpurnius Piso, who was a contemporary and ultimately the father-in-law of Julius Caesar, built, most likely it was him who built this incredible replica of the Getty Villa near Naples. And this is a reconstruction, if you like, a rendering of what it might have looked like. And it was discovered by accident in the 1750s and excavated. And just amazing. I mean, like, these people were not so different from us. They enjoyed a beachside vacation. But this house, which is absolutely enormous, contained within it a working library. We know this because in the scrolls that we've found in there, here's another image, we have found multiple copies of the same text with like revisions and notes on it, right? So like, if you want to show how astonishingly rich you are, not only do you have a library that's full of ancient scrolls, you also have like a troop of philosophers and scribes who sit in your library generating new work over time, right? It's not actually all that different from kind of the venture capital, like seed funding type thing, but they're actually collocated here. So if you wanted to go and speak to Philodemos, you had to go, and he lived in this house with his philosopher buddies and wrote stuff. And of course, this house, this villa, was around for about 160 years until it had a very, 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 very bad day. So on the left, we have a painting of one of the major eruptions of Vesuvius that occurred kind of in the early modern period. And there's actually a fabulous original work in the Huntington Library, which is just down the road here, of another eruption of Vesuvius, very similar to this. And on the right, some photos that I took when I hitchhiked my way around Italy in a previous life. And obviously it has continued to erupt up until about 1944, was the most recent eruption. But the eruption that occurred in AD 79 was kind of less lava and more ash, and it buried, amongst other places, Herculaneum and Pompeii, which we know about so well. And Herculaneum is somewhat less famous, but it's actually better preserved because it was buried in about 70 feet of pyroclastic flow and superheated mud that had the effect of not only killing everyone there, but also sealing the organic material and then heating it to pyrolyze it, which ironically preserved it. So we know of all these ancient libraries, like Library of Alexandria and so on, and they've all been lost, either through fire or depletion or the Dark Ages or whatever. But in the Villa of Papyrus, which is, it's kind of hard for me to point it out here. See if I can pull up a cursor. All right, is that visible? Yeah, okay. So this hole here is the excavated part of Herculaneum, and just over here to the left is the excavated part of the Villa of Papyrus, so right by the town, because in those days no one had cars, so you had to be close to the town in order to get access to labor and whatnot there. And then up here, of course, is the volcano that pushed all the ash down here. And historically, this would have been the shoreline, and this extra land is the result of mostly the eruption that occurred in AD 79. So, if you walk around this town, you can see the ancient wood and the ancient rope and other kind of materials that generally would not have lasted for 2,000 years. And certainly over in Pompeii, they did not, because it was buried under ash instead of under mud. This is a plan prepared of the Villa of Papyrus, showing the tunnels that were used to excavate it. This is actually the first, I learned last night at an event, the first modern excavation of any archaeological site. Previously, they would have dug it up and looted it. This time, they very meticulously dug and recorded the location of everything they found. And this meant that when John Paul Getty got interested in this and decided to make a replica over in Malibu, he could take these plans and basically make replicas of all these sculptures and put them in exactly the same place that they are in the original. That said, as far as ancient excavations go, the villa is still mostly unexcavated and unexplored. It is still buried underground, and the structure itself had multiple levels. Only one of them has been excavated. Almost all of the books were found in one little room over here somewhere. And this is what the excavation of Pompeii looks like today with the volcano in the background. I do recommend visiting it if you ever have the opportunity. All right, so this is what the scrolls look like. So these were discovered, and people initially did not really know what they were. They thought they were lumps of wood or something and threw them away. But eventually someone realized that they were papyrus, which is a reed that's grown in the Nile Delta and processed to form paper, or well, paper and papyrus are the same word, but something like paper. And they were kind of stuck together in a long roll about 10 meters long, about 35 feet long, and then it was all rolled up, and each one is, kind of a modest burrito in size. And then, of course, not only did these scrolls get replaced slowly because they weren't photocopiers back in the day, so they were probably already fairly degraded. They were then crushed by superheated mud, pyrolyzed, buried underground for 2,000 years, excavated, subsequently damaged. Some of them were lost. People tried to unroll them. Obviously, this is so crunched up that unrolling it would be extremely difficult. And that's essentially it. Like this scroll here almost certainly contains around 10,000 words of ancient text that no one has ever read, no one since it was last put back on the shelf. And we have no way of knowing what it is. How frustrating is that? But the reason this exists is because people knew for the last 250 years that maybe someday we'll have technology that can unwrap this. And the cool thing is, we now do have this technology. So enter Brent Seals. Brent Seals is a fellow on the left here. He's a professor at the University of Kentucky. And he got interested in this problem, and he and his students for about 20 years have been working on using certain advanced technology to read scrolls. And so this is a fragment of a Dead Sea Scroll. And fortunately for this, in this experiment, they found that the ink was kind of a metal-based ink, or it had metal ions in it, which glow rather nicely under X-rays. Unfortunately, the Herculaneum scrolls that we have scanned so far do not. They are a carbon-based or a soot-based ink that is written on a papyrus layer that is now also completely made of carbon. So it is somewhat more difficult to read it, to say the least. But this project went on, and then Nat Friedman, who some of you will have heard of, former CEO of GitHub, and then some guy on the right who doesn't use Linux, got involved in this, and Nat Friedman led this. Satya was not involved, and basically proposed a prize to try and garner interest from people like you, right? People like you, people like me, who think this is cool, who think, I know how to use computers, I know how to code, I know how to automate stuff, I know how to process large data files, and I'm obsessed with the Roman Empire. Let's have a go, see what we can find. And so they started this competition, I guess last year, announced it, and they had it was kind of an interesting thing. It was kind of a blend of like the grand prize and then progress prizes that in order to win them, you had to open source what you already found, which kind of made sure that everyone involved in this project was constantly brought up to date with the state of the art of the process. I actually met a lot of these people at an event last night for the first time, and it's amazing. It's actually a very small core of people, like literally a few dozen people got together and figured out how to advance the state of the art of this process by decades in their spare time over the course of a year. So here's a cross-section of one of the scrolls. This should give you some idea for how difficult it is. And actually, the process of reading one of these scrolls using this technique that has been pioneered is first it is scanned in essentially a computed tomography, like a CT X-ray imager, much like a medical one, but much, much higher power. The resolution here is 8 microns, which is 20 times narrower than a human hair, something like that. And then the scanned data file is processed to what's called segment it, which is to say try and unwrap sections of it into contiguous sheets that are flat and then those sheets are read using an AI kind of ink detection neural network to determine where the ink is, and then that's all assembled, and then the ink detection layer is then optical character recognition, but usually by hand or by eye, by experts, edited, and then holes and so on are repaired. It's a very laborious process. And part of what you can help with is accelerating this process, in particular, the segmentation process, which is the process of starting with a file that looks like this and unwrapping it into a nice long, 35-foot long sheet. And as you can see, this is a screenshot from one of my attempts to build a kind of autonomous agent that would trace these layers around the edge of this big gap, and it went off the rails at the right-hand side because I'm only moderately talented when it comes to writing this sort of code. But it is a worthy problem, and we do need to solve it. Right now, if you incorporate the labor and computing, it costs roughly $1 million to segment a scroll. There are 600 known extant scrolls, and probably many thousands more that are buried. This does not scale. We need some way of file segment done to largely automate this process. Okay, and then my personal individual contribution, as outlined here by Ashley Vance, is that eventually I gave up on writing software to solve this problem and just stared at the scrolls for a really long time, which I did. I made a kind of a viewer that allowed me to do some optical, some image manipulation, and then I stared at this file for probably 20 hours. Eventually built an ontology of different textures, and then recognized that one of the textures was ink, and then basically, I'll play this video and I'll give you a bit of a voiceover. This is how it worked. So this is what the raw data looks like once it's been unwrapped. You can see layers of papyrus overlapping each other at right angles. Then you kind of scrub through the layers back and forth. It's the thickness of a sheet of paper, and you see this crackle pattern. You say, that looks like it could be a pie, or possibly an iota ligatured to a tau. So I got out my Sharpie and started scrolling on my screen to pick this up, because it's nice and quick. And then this is the AI-generated image, which obviously overlaps quite nicely with what I saw by hand. And of course, this allowed us to scale this to enormous amounts of text. So we have here, I think, the bottom half of 15 columns of text that were written in this scroll. The scrolls are not read like this, they're read like this. And they are read from left to right, but I'm running this from right to left. And as you can see, some of these sections are very clear, and some of them are very not clear. And we need your help to come in here and refine these algorithms so that we can, first of all, detect the ink, and then second of all, fill in the gaps with some kind of ancient Greek LLM. Because there's only about 50 people worldwide who can actually read Greek well enough to do this by hand. And they're all pretty old. We're going to have to use AI to solve this problem. All right, let's see if I can go to the next slide. No, next. All right, so here are the three gentlemen who won the grand prize. $700,000 split between the three of them. Now, I don't know about you, but $200 and something thousand would be life-changing money for me. So, and Luke in the middle there is 22. He's a lovely guy, but it's kind of derailed his life plan. I met his father yesterday, and his father was like, I don't know how to think about this. My son has dropped out of college. And unfortunately, Yusuf on the left was unable to join the prize ceremony because despite the fact he applied for a visa to visit the United States months ago, the Department of Immigration told him to get stuffed. So that's very sad, but he's still working on it. And then Julian Schilliger on the right has been working on a upgraded, automated, segmenting system. But this is it. Essentially, this is the first time that anyone has ever read this much text, anything like this much text, using CT process data. Not all of it has been translated, but we think that the sections of it basically are philosophy. It's talking about what is pleasure in life, essentially. So maybe it's not the most revelatory text. There's a couple of blog posts out there that say, what would be the most amazing ancient text to recover? But at the same time, the intertextual hints you get from this give you a picture or an insight into the lives of these people who lived 2,000 years ago that we would otherwise never have. We have so little from the ancient past. And this is a chart that I put together to illustrate the point. So in blue, we have by number of scrolls, essentially the entire ancient corpus that has come down to us. One scroll, for reference, is about 1/10 of a novel, about 10,000 words. So it's almost nothing. There's an edition that's put out by Harvard called the Loeb edition, which is translations of ancient Greek and ancient Latin texts, and you can fit all of it on a bookshelf that, I don't know, if you just stack them in front of this stage, it would come from that corner to about here. So like any of you could go and buy these books for less than a new car and read them all in a year or two, and you'd at that point have read all the ancient text that has come down to us via the medieval scribes. And yet we know of relatively undistinguished private citizens in ancient Rome having personal libraries of over 40,000 scrolls, which would be about 4,000 books. Thomas Jefferson's private library was about 7,500 books, which he sold to the Library of Congress in the early 1800s. So this graph here assumes that this library only had 25,000 scrolls, which is probably conservative, and that the scrolls were constantly produced during the period the library operated, around about 80 years either side of the turn of the millennium, and plus some number of ancient scrolls that predated it that had been preserved up to that point, which we know from later attestations did exist at the time, right? Like you could just go down to your bookshop and buy these works. That's probably underground right now. It's probably at most 10 feet from an existing tunnel. It's already been dug. And I'd say within a year we'll have a much improved pipeline that can actually like take one of these scans and produce something like that text with a lot less work. And actually, Elon Musk put in just over $2 million for this year's scroll prize bonuses, which is like reading 95% of one of these scrolls. So regardless of your opinions on Elon Musk, I think we can all agree that he would survive with less money. So you should compete with these prizes. All right, so that's wrapping up the scroll prize. I probably should have mentioned that I studied Latin for 7 years in high school. So like, I knew about this, and I was like, one day we're going to X-ray these things and figure it out. It's kind of crazy. If you keep your ear to the ground, you can see these incredible opportunities. And the grand prizes for these are generous. Like I won a progress prize of $10,000, which I spent on a new computer. Wonderful, but like a lot of the other people who got involved in this project won significant sums of money. All right, so the second section of this talk is going to be about building a better future for all of humanity. And here's another Midjourney generated image of a cool futuristic city. Although I don't know, I kind of like the hodgepodge of the urban environment, but different tastes, whatever. So this is the good news. I kind of alluded to this earlier, but the number of people living in extreme poverty worldwide is around 500 million today, which is a lot larger than I would like it to be. But it seems that number will probably converge to zero in the next few decades. And so we can actually say with relative confidence that the number of human years of extreme poverty that are left to be endured by the human race is a few billion, maybe 10 billion at worst, which is extraordinary, right? Because if you had looked at this graph in 1970, say, or 1980, and you had said, can you put a bound on the number of years that a human mind will have to endure extreme privations and misery, the best answer you could give would be 3/4 of the human race will always be enduring misery, which is a lot better than it was in 1800, when it was 99% of the human race essentially living in abject poverty. But it's not great. And so we are at this point now. We're moving in the right direction. This is extremely encouraging. The vision that I kind of outline here is like the emancipation of every last man, woman, and child on the surface of the earth from condition of material want. And if we eat our vegetables and we do the right things, it will happen in our lifetime. This is the reason why it's occurring, which is explosive economic growth worldwide. It turns out that when everyone gets rich, it's a good thing. Obviously, some people richer than others, but overall, everyone's getting richer. And the main reason this is occurring is that we're getting much, much better at using energy. There is no such thing as a rich, low-energy country. And so the the zeroth order solution to this problem is to take the remaining poorer countries on the left down there and greatly increase the energy that they have available. There are a couple of challenges to doing this, of course. Here's the United States' economy. Here's another chart that's full of text, or say energy budget in 2021. And if you look closely there, you'll see roughly 2/3 of the energy that the US economy consumes comes from fossil sources, which poses two key problems. The first is that it's finite. There's not enough to go around, even though it is fabulously good value to yank oil out of the ground and burn it. It's roughly 100 times cheaper as a source of energy than food in terms of mechanical work that can be applied, which is why we can afford to drive cars around, which are significantly more energetically intensive than like some ancient war elephant or something. But the other problem, of course, is that it's melting the world gradually. The CO2 builds up in the atmosphere, heats the planet. This is actually not necessarily terrible news if you live in a very cold climate, but it is terrible news if you depend on trade and agriculture that occurs close to sea level, which is most of us. And the usual set of solutions to this problem, which are, well, simply stop burning oil, well, we know what that'll do, or we'll force big emitters to pay for carbon sequestration, are also very problematic because, as you can see from this chart, on the bottom right, essentially the corporations and the industries that are responsible for the highest emissions, which is typically materials, utilities, oil and gas, also have the lowest revenue per ton and the lowest profit per ton. And so the actual amount of economic power that is available to sequester the carbon that they emit is on the order of $1 per ton of CO2. And the cost to capture and sequester a ton of CO2 is more like $1,000. So it's not close. It will never be close. The result of forcing these companies to pay to sequester their CO2, even if we were able to do it worldwide, would be that staples we depend on, such as concrete, steel, food, oil, would become completely unaffordable, and obviously result in a reversal of that graph showing number of humans in extreme poverty. So we need some other solution, and really technology is the way. There's three key ways to do this. This is probably the most controversial slide in my entire talk. This is likely to make at least some of you quite annoyed. But essentially, we need to decouple these three problems. We've got a global temperature problem. We have a global CO2 problem and a global energy problem. And so in order to solve the temperature problem, we need to take some of the sulfur that we recently took out of marine fuels, particularly in the North Atlantic, and put it back. Ideally, if we put it in the stratosphere, then we can make do with about 100 times less sulfur, and it'll have the same net cooling effect. But actually, if you look at graphs of the recent temperature rise in the North Atlantic and North Pacific Oceans, it is stark, and it correlates perfectly to the cessation of use of high sulfur marine bunker fuel. And that is because sulfur pollution reflects heat from the sun back into space extremely effectively. It also hurts people, particularly in port areas. So I think overall it's a net win to desulfurize our fuel, but we should take some small fraction of that sulfur and put it back in the stratosphere. And this is not forever. This is to keep a lid on our temperature for the next decade or two, while the other two prongs of this approach get into place. But I think it would be, my personal opinion is it is extremely irresponsible, given that we understand and have this technology, to allow the world's temperature to rise to the point where we destabilize ice sheets and things and cause mass famines. Just today in Ghana, average temperature of 43 Celsius, which is about 110 Fahrenheit. This is the temperatures which are no longer survivable for human life. And with tiny investment, we can keep a lid on global temperature for as long as it takes for us to move our economies away from oil. The second step is CO2 removal. That's most likely the easiest way to do that is via enhanced weathering. So pick a mountain somewhere in an equatorial area, grind it up into dust, put it in the ocean, soaks up CO2 that's dissolved in the ocean, sinks to the bottom. We can yank out 1 or 2 trillion tons of legacy CO2 that we put in the air over the last 100 years. And then the third step is cut greenhouse gas emissions aggressively. So this is done by electrification of our industry, so as much as possible switch industrial processes, switch transportation over to electricity. And then the step that I'm getting to work on at Terraform with this band of killers, it's amazing to get to build your own team. I've never previously gotten to work with people where every single person I felt was like really cool to work with. There was always one person who ruined it. But now, I'm that person. Look at these people. So we're doing synthetic fuels. We're making carbon neutral fuels out of atmospheric CO2. So when you burn it, you're not putting new CO2 into the air. You're only putting CO2 that was already in the air back into the air. And of course, that's a nice idea, but you have to figure out how to do it cheaper than drilling a hole in the ground, which sounds impossible, but actually drilling is really expensive. So it might be possible. This is our facility. About 15 people in this photo. And yeah, big news coming out this week. Stay tuned. So the only reason this is possible is that the other thing that humans do with silicon, other than run Linux servers, is solar panels. And since about 2009, the learning rate for solar has been about 44%, which is to say that every time production has doubled, the price has come down by 44%. And currently production is doubling roughly every 2 years, although that is gradually shortening, which is the same as saying that the price for solar energy is coming down by about 20% per year. This is extraordinary, right? Like, we live in a world where we're enduring insane inflation and where everything else, labor, materials, land, etc., is becoming more scarce. And at the same time, energy, this thing that is unlocking global prosperity and curing poverty and enabling us to get beyond fossil fuels, is coming down in price by 20% per year and doubling in volume every 2 years. It's mind-blowing. And so if any of you are thinking of starting a company in the hardware space, think of something to do with solar power that is not yet being done. There's about 15 or 20 different industries out there that need to be disrupted with solar. Ours is just one of them. So I don't want to give you guys the hard sell too much, but this is our product. It takes in power and water. It produces hydrogen in the electrolyzer. It captures CO2 in the direct air capture area and converts CO2 and hydrogen into natural gas. And critically, on the bottom right, it makes money. How much chemistry do you guys want? I mean, like, I guess the interesting thing I can say about this without going too much into high school chemistry is that the science behind this process has been understood since at least the late 1800s. It was put into mass scale in Germany in the 1920s. The Nazi war machine was run on synthetic fuel made from coal, which is a fossil fuel, but they made kerosene and gasoline from coal. And this process is not that different to the chemical synthetic fuel processes developed by BASF at Leuna and other chemical plants, which still operate to this day. So it's not like this has to be invented from whole cloth like fusion. We just have to figure out how to take the coal out of the process and put solar power in, which is what we're doing with the direct air capture. All right, and here's the workshop. So for most of my career, I had to work in front of a computer and, you know, in a room full of people in front of computers and keep the kind of the workshop work to the garage at home. But now, I don't hire a single software engineer. And my life is so much happier. Software engineers are so expensive. Maybe one day, but mostly it's just machinery, which is a lot of fun. And as you can see, this is not the prettiest building on Earth. Bits of the ceiling are falling down, but yeah, it is what it is. Our machines are meant to work outdoors anyway, so if it rains on them occasionally indoors, well, it's not a big deal. So I'll just show you some more photos of hardware. This is the reactor that converts CO2 and hydrogen into methane. The reason I show you this is that we will use these things on Mars one day, because Mars does not have naturally occurring hydrocarbons, and we do need hydrocarbons to make plastics, amongst other things. So we'll have a system like this on Mars, and that's Dr. Nadin, who's our chemical engineer. And this is our electrolyzer stack. So it's critical to be able to make cheap hydrogen, and we figured out how to do that. Again, I'm not going to jump the gun on our announcement later this week, but if you follow green hydrogen, you'll be quite surprised at our numbers, I'll put it that way. And then this is direct air capture, where, again, we're breaking new ground in terms of being able to yank CO2 out of the air cheaply. This is the vision. So I mentioned earlier that oil and gas is about 100 times cheaper per calorie than burgers, burger and fries, which is a good thing because on average, Americans consume about 100 times more energy in the form of electricity and oil and gas than in the form of food, which is one of the reasons why our lives are awesome compared to our ancestors who, if they needed mechanical labor, had to either use their own muscles or whip an animal. But it also means that the solar panels and the solar synthetic process is significantly more efficient than plants. at capturing CO2 from the air and then reducing it into useful chemicals, like 1,000 times more productive. And that means that we can actually have these two processes and they can coexist, right? We can have 90% of the Earth's surface essentially restored to whatever antecedent state we prefer. And actually, when we think of like wilderness, actually what we're typically thinking of in this country is like actually a fairly carefully curated garden by indigenous American people. But whatever aesthetic we'd like to build, and then with a modest addition of solar arrays, we can actually get all the energy that humanity will need, unless AI gets truly out of control, to supply the energy that our industry needs in relatively compact cities. And actually, the neat thing is, you can put solar arrays out in the desert, just across the mountains here in Mojave or whatever, and the shade that they put on the ground can actually reverse the desertification that has only occurred there in the last few thousand years. So 10,000 years ago, during the last ice age, all our local deserts were actually pretty lush. This is a rendering of Mojave in 2050. And so lastly, I'm going to talk about the Roman Empire on Mars, and which of course is a reference to building cities there. But mid-journey once more with the goods. So this is a photo that I took back when I used to fly planes of the Grand Canyon. And the human eye, connected to the visual cortex, is pretty extraordinary. So you can look at this picture, which is a two-dimensional image, and if I gave you a piece of paper and a pencil, you could probably draw a pretty accurate map of the Grand Canyon in this picture, including the various terraces and how they connect to each other, the more or less impassable cliffs, where the water flows, all that kind of stuff. You're able to deduce geographic information, topographic information from a single image, just on the basis of shading and shadows and texture. I thought, if human eyes can do it, why can't we train an AI to do it? It turns out it's really hard. We've been evolving for billions of years. But this is the best image we can get of the planet Mars from Earth. This is with the Hubble Space Telescope. And there's a lot of detail there. You can see some craters and the South Polar Cap and a few other details. But if you wanted to do a high-resolution hydrology study, you're kind of out of luck because you don't have the data. This is the best we can do from Earth. And that's pretty good. Actually, if you go up to Mount Wilson, you can rent out a telescope there for an evening, and if Mars is close by and you look through it, you can see it about as well as this, because that telescope is the same size as the Hubble, which is kind of amazing. Like, there's more detail there than you can see on the moon with a pair of binoculars. So, yeah, big telescopes are cool. But we recognized this problem a long time ago. So NASA sent Mariner 4, took these photos of Mars. Kind of craters. At the time, actually, a lot of people thought that Mars had like canals and forests and stuff. So this was like kind of a downer on that. And then they sent Mariner 7, which took this photo. Obviously, they got a lot better at building satellites with cameras on board. I wonder why. In the 1960s, of the edge of the South Polar Cap, which is pretty extraordinary. And then this is a photo that's actually taken by an engineering camera on the Perseverance rover as it came into land on Jezero Crater. So this was taken just a minute or so before the previous photo of the alien spacecraft landing. And that disk in the foreground here is the heat shield that has fallen off. And then this shape here, kind of this arc here, is the edge of Jezero Crater, which is about 100 kilometers across. And in ancient times was a lake, because these features down here are the remnants of an ancient delta. And then this is the horizon of the planet in the distance here. I think it's a cool image. And then here's a photo taken by Mars Reconnaissance Orbiter of the rover coming down under its parachute. Again, here's the delta feature on the left, coming down to land. That's kind of cool bragging rights. Like JPL, you're like, yeah, I took a photo of my Mars rover landing on Mars. Like, that's kind of cool. And then another Mars orbiter, more recent one called Mars Global Surveyor, had a laser altimeter and made this data set, which has about a 450 meter resolution, which is great. So on the left, you can see some giant volcanoes, and on the right, some actually almost as giant volcanoes. The one on the left, the big circle, is 24 kilometers tall. It's about 3 times taller than Everest, which is pretty cool. And then these giant holes, particularly these two ones on the bottom, giant impact craters from the Noachian period, like back just after the planet formed. But Mars's surface has never been really comprehensively resurfaced as Earth has. So you can see these ancient scars. And I got interested in terraforming. And so the first step to terraforming, of course, is to perform a hydrological survey. And this is a simulation that I did of of where rivers would form on Mars based on the molar data set, which I just showed you. And what you can see is these like red lines showing lots of flow in a narrow area. And if you look at the visual imagery there, you can actually see canyons. Like Mars has had water flowing on it in the past, and it cut these holes. And for a planet that's made almost entirely of craters, the drainage systems are actually pretty rational. Like there's long rivers and stuff. It's not just like the Canadian Shield with a bunch of like muddy lakes and things all over the place, which is pretty amazing. And then there's an ocean in the north, of course. But this is not good enough. This is not good enough. Because when I went and made some renderings of what a terraformed Mars would look like, it's actually kind of cool, like little islands and bays and so on. But it's all kind of higher resolution, like higher altitude. Like the camera altitude in these images is much higher than like a jet, like you're flying over to Australia or something. And if you zoom in, you can see the pixels. It's very unsatisfactory. And so I embarked on this project to try and make a higher resolution map, because I felt that if we could make a beautiful enough rendering of what Mars would look like when it's terraformed, and there's that giant volcano again here on the right, it would motivate people like you to be like, this is something we should do. A terraformed Mars, a Mars that's green and blue with clouds and lakes and life, would be the most beautiful thing that humans have ever built. So we go back to this camera image here. It turns out that the orbiter that made this image has taken so many photos of the planet that there's now a 5-meter resolution black and white data set of the entire planet, which you can download from the Murray Lab at Caltech. It's only 8 terabytes. The planet's kind of large, of the entire planet. And because the orbiter's in a sun-synchronous orbit, all the photos are taken with consistent lighting. Now, so if we train an AI to deduce topographic variations on one of these areas, it will work on all of them because the lighting is the same. So that's what I did. On the left, we have the high resolution optical black and white image. And on the right, we have the topographic image rendered as a relief map. And this particular image is about 1,000 kilometers wide. And so the resolution here is actually the laser altimeter data set. And we're going to zoom in on this crater in the middle, just here. This is Jezero crater, which is where the rover is. So we're going to zoom in on this crater. And this is about 500 kilometers wide, 500-meter resolution. This is the limit of the resolution of the laser altimeter. Every subsequent image after this, the AI takes the best topographic image we've got, plus the optical image at twice the resolution, overlays them, and interpolates using this trained rule. And we get this fabulous detail that otherwise does not exist in any form. Actually, that's not true. In this particular place, NASA spent millions of dollars doing stereo mapping, which you can use for ground truth. But for the most of the planet, that's never been done. So this is the delta feature. You can see the river flowed in from the left and then spread out into this lake on the right. Continue to zoom in. On the left, you can now see some sand ripples on the optical image. Those are sand dunes in the ancient channel. And we continue to zoom in here. Some of those sand ripples are now visible in the topographic data set. And actually, this coincidentally happens to be the place where the Mars helicopter crashed about a month ago, landing on these sand ripples, because it's very, very difficult to use stereo control over sand because it's so uniform in color. You don't know where you are, you run into it. And then the little helicopter died. Oh, man. Anyway, we're zooming into the pixels here. So this is the vision. We build the rad city on Mars too. Anyway, to wrap up, I'll say if there's anything that pulls all these ideas together, it is if your vision for the future includes elements that will not occur by themselves, you have to build them. Right? No one else is going to build them. The frontier is inefficient. If I had not started Terraform Industries, no one would be doing synthetic fuel this way. If I hadn't done this Mars mapping, no one would have done it. So, yeah, think about your vision for the future and the missing pieces, and the ones that don't yet have an economic imperative. All right, that's the end. I'm going to take some questions if that's okay. But thank you for your attention.
Thank you, Casey. That was quite enlightening. So Bala's running around with a mic. If you've got questions, raise your hand while he's doing that. I think you will be the only husband and wife pair that are part of the SCaLE family with a SCaLE jersey. A couple fun facts. Casey, I believe Casey's partnered with a keynote we had 4 years ago, here in this room. So it's the first husband and wife keynote couple you've got. But thanks again for joining us. He wants you to show the name. And then I think, other little fact, I think there's some folks on our AV team that helped write the flight software for that helicopter that crashed into Mars that you were talking about. So lots of HEPL folks on the team.
One of the challenges, of course, on Mars is that it's roughly 20 minutes light time away. So the helicopter has to be completely autonomous. And it also has to be, like, all the control hardware and software has to weigh like a couple of dozen grams.
So if you want to learn about that, Michael Starch has given a couple talks here at SCaLE about that. You can go back and look for them on our YouTube channel. But I'm looking around the room. Bala, do we have a question?
Anyone, please.
So there's a new technology that I read about that seems very promising. A company wants to produce nickel-69 batteries that will decay into copper, and they'll last, they say, 50 to 100 years.
Yeah.
So if you could eliminate the need to deliver power, that would, I think, have a great impact on the world to eliminate the distribution.
Yeah, so the technology, if any of you want to look it up later, is called beta voltaics. And there's a handful of nuclear species that decay via beta decay. And so instead of using solar energy to kick your electron across the Fermi gap in a solar array, you can use radioactive emission to do that. And they've actually been employed in pacemakers. There's some people walking around today that have radioactive beta voltaic battery in a pacemaker, but it has not yet been reached major commercial scale. So I wish anyone who's trying it well. I think it's a neat technology. The major challenge, actually, if any of you want to solve it, is current density. So an 18650 cell, such as you might have in a laptop or a car or something, electric car, can discharge essentially all its power in a few minutes. And while it's true that the beta voltaic battery can last for 100 years, the amount of current that it can actually produce at any given time is pretty small, because the process of emitting that beta particle also makes a lot of heat, and so it gets too hot. Anyway.
You were showing us that graph of sort of energy distribution and usage in our economy. Is that is that pre-AI or does that include AI?
That's from 2021.
So that's pre-Chat GPT is what you're telling me, and now the bubble for Microsoft or OpenAI is just like that much bigger. Or?
Well, there's a lot of kind of chit chat now about kind of growing demand for power, partly as a result of U.S. reindustrializing after 30 or 40 years of not much, and partly as a result of kind of previously avoidable and now more or less unavoidable drag on deploying more grid transmission power, but mostly AI data center demand. So we're talking like gigawatt scale data centers going in, and you can't just plug a gigawatt scale power cord into the grid and expect everything to work right. So I think it'll mostly be solar and batteries kind of islanded beyond the grid to do that.
I know what Edlin charges us for a power outlet in one of these rooms. I wonder I can't imagine what they would charge us for a gigawatt plug versus.
Well, so a power outlet, like a typical power outlet in the United States, is about 1.2 kilowatts. So a gigawatt's about 1 million of those.
Cool. So I'll put a donation box outside.
So my question is, how would you terraform Mars if you get to set the plan?
Yeah, so actually I'm going to a workshop next month to talk about this. God, that sounds like a dream job. They're not paying me. But it seems to me that to terraform Mars, you have to solve the heat problem and you have to solve the atmospheric composition problem. And the heat problem is most easily solved with an array of millions of relatively small scale, maybe the size of this room, solar sails. So you could mass produce those in a factory in Taiwan, say, and then just hurl them into orbit with Starship, and then they'd fly from low Earth orbit to Mars and then hang out there and essentially make the sun shine on the dark side as well, to heat the planet up a bit. But then you can have a warm, poisonous planet instead of a cold, poisonous planet. So you still have to fix the chemistry a bit, and that's I think that's a much more involved problem. But I think step one is the heat problem. So just getting some ideas for slides I can add. So
I have several questions, but I'll pick one. I heard a proposal back in the 70s of dropping tailored algae into the atmosphere of Venus
Yes.
to make it nice.
Yes.
Does that seem at all plausible to you?
No.
Okay.
I mean, I'm aware of the idea. It's a cool idea. The problem is that Venus has almost no water in its atmosphere, and algae require water to live. So you would end up in a situation where you would, if the algae could survive, they would deplete what little water remains and not really affect the climate. Terraforming Venus is almost certainly much more difficult.
Okay. You
Yeah.
didn't mention nuclear. You must have an opinion on it.
Nuclear. Well, so I'll preface this by saying that I taught nuclear physics at Caltech for a couple of years, including in the lab. And I have a tritium source in my bedroom that glows green. And that's completely legal, by the way. You can just buy them on Amazon. So I'm not anti-nuclear in any sense of the word. I think technology is interesting, but I think that since the 1950s, it's been extremely challenging to develop nuclear power plants that are kind of economically compelling, and particularly now against the backdrop of solar falling 20% a year. It's very difficult. And of course, nuclear and solar are a little bit different in some ways in that solar works during the day and nuclear works most of the time, but essentially you can pair your solar array with batteries, and then that will provide as much power as you're prepared to spend on batteries, essentially indefinitely. And you can do that in a few months. And right now there's not a single nuclear power manufacturer, like nuclear power plant manufacturer in the United States that can deliver you a nuclear power plant in like 10 years. Let alone at the scale that we'll need. So to do the synthetic fuel thing, we'll need 400 terawatts globally. 400 terawatts of nuclear is more than 1,000 times more than is currently deployed. So I don't know if there's enough uranium floating around. And if we wanted to do AI at the limit, it would be more like, I think it's 173,000 terawatts of solar insolation on Earth. So that's the problem. Any other dreams that I can crush? Yeah.
I mean, I think I saw Hawaii is like almost primarily powered by solar plugged into a battery at this point, or
yeah, a
parts
lot
of
more
it.
than other places.
Yeah,
There's a handful of, so like a common canard against solar is that it can only provide a part of the market, or it needs to be paired with wind, or you need to have like a 1,000-mile transmission line to make it work. But there's quite a number of island nations now that are essentially solar plus batteries, and yes, they don't have like a massive industrial base, but they can kind of give you a glimpse into the future because the economic conditions that exist in these places is very similar to the economic conditions that will exist, say, here in 5 years' time. But anyway, Los Angeles is almost all solar during the day, even now in early spring. Anyway, you can look it up on the California ISO website for yourself, and then probably 10 or 20% batteries overnight as well already, and there's I think six gigawatts of solar in the Mojave, and another 8 gigawatts in the pipeline. So we're not done yet.
Cool. Awesome. Well, thank you again, Casey, for joining us.
Thank you.
And